Here we go. So we were here. We were talking about the EM spectrum, about the properties of stars. We had been looking at the HR diagram. You will not have questions on your quiz over the HR diagram, but you will have some questions over the other pieces on this sheet and on the stars notes that we're taking today as well. We want to get through this, though, so we understand it and we can apply it. We will be doing more of this later. We do not need Chromebooks out right now, so you guys can go ahead and close your Chromebook, though. I appreciate that. Thank you so much. All right. So yesterday we were here together. We made it through 5, 6, and 7, and those are really the skills part, right? I was talking to a lot of parents during parent-teacher conferences. I have not updated my percentages, and I will do that soon. But I was talking to a lot of parents, and they were saying, do you do a lot of labs in earth science? And I'm like, well, not in the space part, because it's kind of hard to do labs in the space part, right? We can't collect data, can't go out to the stars and take their temperature and those sorts of things. But we are doing science skills. We are reading graphs. We are understanding and applying what we know. That piece of it, are you doing all right?
Yeah, she said I'm a little over, but not enough to go home.
Awesome. I'm glad you're here. That makes me happy. I'm glad that you got that checked too. So we're going to start here, making sure that we know how to read and understand these graphs. So let's take a look really quickly, friends, at questions 8 and 9. Question 8 says, in astronomy, I'll have this paper out, right? Yes. In astronomy, luminosity is the total amount of energy emitted per unit time by a star. What does that mean? They shine, right? Stars shine. They give off energy, light energy. We've been talking about that energy for a lot of days, okay? Luminosity is basically how much energy are they giving off. That's really all it is. Another way to think about it is brightness. If that makes a little more sense to you, how bright the star is. Here's the question. Why do red giants have a higher luminosity than a white dwarf, even though they put out less energy total? Idea?
I'm just going to assume because they're bigger, that means they have more, like they have more energy, per their whole entire mass. Because if you have a smaller star letting out a ton of mass, the red giant can still be letting out more mass, or letting out a ton of energy. The red giant can still be letting out more energy because it's bigger.
Right. That's
exactly. It wouldn't be letting out more for square mass.
It's just got a whole lot more space, a whole lot more surface area. Okay, that's exactly right. Nice work. So red giants have lots of surface area. And because they have so much surface area, they are actually giving off more energy because there's just lots more space for it to be given off from. Lots of surface area means a higher overall luminosity. Okay. More surface area, higher luminosity. I feel like 8 and 9 should be flipped because 8's the kind of big thinker question. Question number 9, think about the colors of the rainbow. You've got this one. If red stars are the lowest temperature, what do you think the temperature is of a blue star? Go, Mariana. Oh, go, Hannah. Or you guys can say it in unison. Go ahead. Blue is what? Highest. Absolutely. Yep. Blue stars are very hot. I feel like we talked about this yesterday too, right? Were we talking about if you turn on a water faucet, if you go into a restroom and you're turning on the faucet, you see a red knob and a blue knob, what do you normally think? Which one's going to be the warm one? Red, because we've been conditioned to think that, right? Red is hot and blue is cold, right? In art, they talk about the warm colors and the cool colors. The warm colors are which ones? Red, yellow, orange, and the cool colors are the blues and the greens and the purples, right? Yeah, that's what we're conditioned to think. That's what we think about. But in science, it is actually the opposite, right? Red is actually the cooler of the stars. We looked it up, though, yesterday, and it's still pretty hot, right? Thousands and thousands of degrees. But blue stars are even hotter. The one way that I know to think about this that makes good sense, if you've ever looked at fire, if you've ever like seen a campfire or lit a match and looked at the flame, the top of the flame is red. Does that make sense? But if you look really close to where the fire is actually burning, where that object is burning, the flame is bluer or even white, okay? Because that's the hottest part of the flame. So get that in your brain. It's opposite of what you've been conditioned for many years to think. So I just want to make sure you know that. Questions about this? Are we good? Hearing no objections, you can put that piece of paper away, pull out your star notes, because we got to do that today too. We're just kind of picking up some pieces here. We'll talk about that just in a second. Yep. Remind me right after we do this, and then we'll talk about what to study. We'll have a test in like a week and a half. Yes, for sure. We'll make a little list of what to study for this in just a minute, though. Yeah. All right, we're going to do this last page. Yeah, Drew, what's up?
I don't think I have.
It's from forever ago. But I got more over here, so here you go. The rest of this is up. Is that yours? Is that his?
This is mine. I'm just telling you this happened.
Oh,
Yeah,
yeah, maybe you weren't here the day that we started. That's okay. Yeah, so we'll fill in. Drew, remind me, and we'll fill in to get more of it, okay?
All right.
We are right now, ladies and gentlemen, for those of you that have been here for all of these notes, we are at the 4th spot, the classification of stars. There are lots of different ways that astronomers classify stars. We've talked about some of them. We haven't talked about others. We're just going to make a list of them and add some pieces right now. So the first one, the first way that we classify stars is by their color. And color is related to the what of the star? We talked about that yesterday, I think. The temp, yep. And we talked about that like a minute and a half ago. Yep, color and temperature is one way that we classify stars. Okay? For sure. Our star is yellow. It's a yellowish star. The temperature is on the order of 5,500 degrees Celsius. Pretty warm. Okay? Pretty warm place to be. Yeah. What? I don't think so. I have it written down. I mean, it's only going to be 273 different between Kelvin and Celsius. So, about the same. Yep. Just a friendly reminder for us that red is going to be low temp. Blue is high temp. We know that because we know that blue light has a higher what? Frequency, and also has a higher energy. We're going to just remind ourselves of that so we don't forget. It's also got a high frequency. It's got a high energy. And it has a low what? It does, yeah. Because frequency and wavelength are always opposites of each other, right? So we can fill in the red one as well. So it's got a low, high. What goes in those little spots? It's got a low temperature because it has a low frequency. It's also got a low energy and a very high wavelength. You've got it. Yeah. So color and temperature, absolutely one of the ways that we classify stars. Another way that we classify stars is by luminosity. Or you can describe that as brightness. They're not exactly the same, but they are similar enough that we're going to kind of describe them together. Okay? Brightness is affected or changed by two different things. Changed by one of them I think we talked about yesterday. If I take a flashlight and I shine it in your eyes, it's going to look a little different than if I walk down the hallway, right? What am I changing there?
Distance.
The distance away? Yeah. So brightness is going to be affected by the distance. And the brightness is also affected by the mass. That means how much stuff there is in the star. Drew, did you have a question or were you just going to add something? Did you have your hand up or was I dreaming? Oh, okay. Just stretching. Okay. I just thought I saw your hand. Sorry. All right. Classification of stars is also dependent on, or another way to classify them is by size. So literally, what is its radius or what is its volume? How big is it? Is a star that is very, very massive also always very, very large? Not necessarily. You can have two stars with the same mass, one that is gigantic and another that is really, really small. It's just that all of the stuff in that star is packed down a lot tighter. Does that make sense? Does anybody know the term for that? It starts with a D.
Density.
Density? It is. Yeah. The same amount of mass in a different volume means that we're changing its density. Yeah.
Wouldn't size also be absolute magnitude?
Say that one more time.
Wouldn't size also be absolute magnitude?
Magnitude is also brightness and luminosity. Yeah, that's also related right in there. But we could totally add that in there. And those three things, they're a little bit different, but for our purposes in here, we're going to call them about the same. Okay? We'll get into it a little bit more, but not a lot. So the funny thing about, so size, again, I want to make sure that we write down that size, the radius and the volume does not dictate the mass. Okay? Because if the density is different, then the size will be different. Okay, so it's just literally how big it is. For example, our sun is kind of a normal sized star right now. It's in the, what is that line called in the HR diagram that our sun is a part of? Main sequence. But we're not going to stay in the main sequence forever. We'll talk about this in the next few days. We're going to move from the main sequence. Our star is going to become a red giant, but it's not going to gain any more mass. It's going to have the same amount of mass. It's just going to get bigger. Okay, it's kind of weird. But it's just going to get bigger, so that mass is just going to expand. So again, size does not dictate mass. Question? Yes, you may. Yeah. Speaking of mass, that's another way to classify a star. So the mass is how much stuff is in the star. And that's usually pretty consistent throughout. Okay? There are a couple of times when the mass of a star might change due to explosions and things like that. We'll get there. But the mass is based on gravitational interaction. What does that mean? Gravity's the thing that pulls stuff together, right? Gravity's the reason that we exist and that our sun exists and that our solar system exists and that our galaxy exists. Okay, gravity pulls it together, okay? And not only does mass, is it based on gravitational acceleration, but it also determines, and this is an important piece, the life of a star. Thank you. Question. Which kind of star do you think will have a longer life? A big star, a massive star, or a less massive star?
A less massive.
Yeah. I don't know if everybody said that, but I heard a lot of people say less. The less massive the star, the longer its life will be. The less massive the star, the longer its life will be. Let me write that down and then I'll answer. Is that okay? I just want to make sure I have it written down. So the less mass that a star has, the longer its life. Okay, large mass stars have a shorter life. Yes, ma'am.
So then, does our sun have, like, is it massive or less massive?
Our sun is right in the middle of the kind of general scale of massiveness. Yeah. So it's not enormous and it's not little tiny. It's like literally kind of middle of the road. 50th percentile, if you will. Yeah. Yeah. And we will talk next week about what would happen to a less massive star, like kind of, us or smaller. What would happen to a big old star, much, much bigger than us. So we'll kind of look at like the different paths that life can take. Okay. All right. And there's one more. It's one that we've talked about before. One other way to classify stars. It has to do with these. Do you remember what we were looking at when we used these things, Beth? What were we looking at? The elements in the star. Yes. So the one other way that we're going to talk about to classify stars is by their chemical composition. Yeah. What elements are in a star? Okay. How are we doing? We okay?
Yep.
So far, so good? All right. The capture question that we've got today is 2.8. It was intended to be used at the beginning of the day after we had done this yesterday. So don't put this away because it's going to help you. We're just going to kind of reiterate things. I'm going to put the question up real quick. You okay, Haley?
Yeah.
All right. So here it is. You're going to get your capture questions out. This is 2.8. It's going to be pretty easy for you, I would imagine. But let's just reiterate it. Write it down one more time. The more you write it down, the more you review it, the better you're going to remember. Yes, ma'am.
Can I go get my notebook?
You may, yes. Name 4 different characteristics that astronomers use to classify stars. Oh, wait, there were more than 4. You can add them all. We're going to add that list. So go ahead and write stuff down right now. We'll discuss it in just a minute. Take a look at your star notes. The story of the photon. Do you remember with Fina and Heidi and Heisa? The emission spectrum stuff. So on that EM spectrum sheet, the one that we finished up yesterday, we will not go over, like this will not be on the quiz. That'll be on the next test, but not on the quiz. This side you do need to know. Because remember, I think I told you before that there will be a question. Spoiler alert, there will be a question that looks like this on the quiz. Okay? So I'm telling you what one of the 4 questions is. You're welcome. And then the other thing I would make sure to look at are the capture questions. I put those on Canvas, so they're there if you need to look at them. Okay? If you don't have them written down, you were gone one day, or you just need to double check, they're all up there as well. Sound good? All right. Excellent.